This is OXDF, and I'm looking at the Shellcode primer, part of the Sans holiday hack. Let's make this a little bit bigger. And this is an interesting challenge where it talks a lot about how to make shellcode, which is a really complex topic, and they do a good job of breaking it down into steps. There's not a really good way to show those steps in a blog post, but it might be interesting to walk through it in a YouTube video, so I'm going to try that. If you you can check this out at tracer.kringlecastle.com and walk through it yourself, and I'd recommend that. But we'll go through it here as well. So in this primer, they've got us set up where we can write code in this window. It'll display a little bit nicer over here, and then I can execute it here. So the first step one of the challenge here is just to run the code they already have and to look at what it's doing. So when we hit execute, you can see it pops up here, and so you can actually step through here in the various steps. So the first thing it's going to do is move 0 into RAX. We can see before that RAX had some pointer, and after RAX is 0. Next step, moves 1 into RBX, etc., etc. Here we're moving 6 into RBP. We push this thing onto the stack. So the stack was here for 55B8. 55B8 is now down 1, and our 1, 2, 3, 4, 5, 6, 7, 8 is there. Also, RSP has now changed because RSP is what points to the top of the stack. And so it is now 8 less. If you think of the stack, the addresses go up as you go down. So when you push something else onto the stack, if we put something else up here, when the stack pointer was here, it has to subtract 8 to go to here, and that's exactly what happens. We do the opposite here to pop RAX. So now 1, 2, 3, 4, 5, 6, 7, 8 is in RAX. It's no longer on the stack, and it actually is in memory, still sitting right here, but we've just moved the stack pointer down, adding 8 to it, and so effectively it's gone. So anyway, that's basically what we have here. We don't need to step through every step of it, but we can go to the next one. So loops. Basically, we don't have the concept like in Python of a for loop. Instead, what you do is you move 5 into RAX, and then you have these labels. And so we're going to decrement RAX and then jump non-zero to top. Decrement RAX, jump non-zero, etc. until we leave the loop. There's actually no need to change this code either. So step 2, we get to just execute. We can step through and see. So RAX, here RAX has something random in it. We put 5 in there. We decrement it. We jump. If it's not equal, we decrement, etc. When we get here, we decrement down to 0. Jump not equal on the short, and then we move to the return. So that moves pretty simply, basically what you'd expect from this loop right here. We'll move on to the next one. Now we're going to start writing some of our own code, I think. We'll remember, let's see, comments are semicolon. Let's see what we got here. The first thing they want us to do is literally just to add a return statement. So we'll do return, comma. I don't know if we need the semicolon or not. Let's see. And we will execute it. And we returned. So that was easy. Returning a value. In assembly, if you've watched any of my my reverse engineering videos or blog posts, we're dealing with registers. There's all these different registers. In this case, since we're dealing with a 64-bit system, we've got 64-bit registers. The return address is typically put into RAX. So when a function's done, you put the value in RAX. They're talking here about how we're going to use the move instruction for that. So if we're going to set RAX to 1337, we'll do RAX, 1337. In assembly, universally it goes, the thing that is going to end up with the value is the first thing, and then the other thing is here. So when we move RAX 1337, that means moving 1337 into RAX. If we were going to subtract RAX, RBX, that would subtract RBX from RAX and store it in RAX. So the thing closest to the instruction is where the result ends up. So in this case, we're going to end up with 1337 in RAX, and then we're going to return just like last time. We can execute this. We can see, congratulations, you've completed the return value. When we get to here, RAX is 539, which is 1337. All right, going to start getting more interesting here. Now we're going to start looking at syscalls, and syscalls are interesting because this is how we actually make use of the system API. Let's see. I believe this is the Chrome one I really like. Yeah, this is a good document. I use this all the time when I'm doing like a flare-on challenge or whatever. Let's see if we can make it a little bigger. Ooh, not quite that big. Okay. Yeah, here we go. Okay, so we'll come back to that in a second. So to perform a syscall, what you're going to do is, and this table actually makes it very easy to see, you're going to put the number, the syscall number, into RAX. So you can see that here. And then the various args that call may take get pushed into, if there's, depending on how many there are, first RDI, RSI, RDX, R10, R8. I guess R9. And most of them don't go that far. So, and then you call syscall to execute it. So, come down here, we're gonna try to call sysexit, and we're gonna call it with the exit code 99. So we want the value to be 99. So we need to set that up. So we'll come in here and we can say, is this exit thing? No, so let's just search for exit. Exit. So exit is syscode 60 or 3C, or OX3C. And then the first column is the error code. And remember that is RDI. RDI. So we need to put move RAX, OX3C into there. Now we need to do move RDI, 99, because that was the value we wanted to return. And then we do the syscall here. And so you can see over here it looks nicer. We're going to move the value into RDI. We're going to move RAX, we're going to set RDI, and then we're going to make the syscall. And when we execute this, great job. We're going to come back to that, but process exited cleanly with exit code 99. So very cool. That was the goal. Calling into the void. What are we going to do here? No need to modify. We're just going to push a value to the stack and return. Okay. Oh, I know what they're doing here. Okay, well, let's take a look at this. This is interesting. So let's see. We are going to push the value 1, 2, 3, 4, 5, 6, 7, 8 onto the stack. So if I talked about this earlier, effectively the stack is, here it looks like the stack's actually moving down. What's actually happening is, so RSP is pointing here. RSP, we subtract 8 from it, so now it's pointing here, and we put that value into this memory. So this right here is actually the same address from here to here, but now we're just, one higher on the stack, and there's our value. Now when we call return, return effectively is going to do two things. Well, it's going to pop the top value off the stack, so the 1, 2, 3, 4, 5, 6, 7, 8, into the instruction pointer. And so you can see that actually shows up as the next instruction here. And so RSP is going to grow by 8 because that instruction address is actually still, or not instruction address, the 1, 2, 3, 4, 5, 6, 7, 8 is still sitting here on the stack, but we move the pointer down so it's effectively, gone from the stack. And now we are going to set the next instruction to this thing we popped off the stack. So, okay. So you have this real challenge. Let's see, what are we doing here? Yeah, okay. So we have this real challenge. And the challenge is that when you run shellcode, so when you run a program, right, you have functions and they know where they live in memory, and the compiler handles making sure that whenever there's a jump or a function call, that everything is set up in memory the right way. If you need to access a static string from memory, those addresses are put in a way that it makes sense and it's held there and everything knows where it's going. When you just inject some shellcode into memory, usually, you're doing some kind of buffer overflow where you're capturing, you're putting the shellcode here and then you're jumping to it. And you have really no clue where in memory you are other than relative to yourself. And so what's useful here is we need some way to get a hold on ourselves and to know where we are, especially if we want to start putting like static strings and stuff in there, which we'll do in a minute. So what are we going to do here? We're going to pop we're going to make a call, and then we're going to pop the address after the call into RAX and then return. So let's see. We are going to call place below the NOP. That's this. And then the thing we're going to do here is we're going to now pop RAX, and then we're going to return. So this is pretty simple to write, but the whole point of this is let's check out and see what happens. So we call our address, and then the next, now you'll notice, this is interesting because, let's get out of here. We'll come back to it in a second. Whatever this is in memory, we aren't going to know, but the address of place below the NOP is not very far. It's only going to be a few bytes, beyond this call instruction, right? It's actually, in fact, it's going to be the length of the call instruction plus one more byte for the NOP, and then now we're at the next, at this label. So that's why you see when we make this call here, the address is leet 000, and we end up at leet 0006. We didn't travel very far. But what's cool is you can see when this happens, if you look on the stack, when you make a call, what happens is the return address gets pushed on the stack. So the next instruction after this that would have been called if it weren't for this being a call gets pushed on the stack. And in that case, that's the address of the NOP, the leet 0005. And so here we are at leet 006, and we've now got leet 005 on the stack. So if we pop that off into RAX, we've now got the address of that NOP sitting in RAX. And we've managed to get a pointer to that thing that was in our shellcode, which is going to be really useful again in a minute. Hope that concept makes sense. Let's see. Let's go. We'll see it here. This is going to make more sense when we do it here. So this is going to be a good place for a call. We're going to, let's see. This is literally the string hello world. We're putting it right there. This would be a good place. So basically what the question is going to be, can we get the address of this string? I believe that's, let's see. Okay, check if I can see if it's an RX. Okay, yeah. So we're going to come over here and we're going to do call label. And then we'll come down here and we'll do label pop RAX, and then we'll return. I believe that's exactly what they want us to do. And so let's watch what happens when we run that. So the first thing we're going to do is we're going to call our label. And so that's just going to jump us forward a little bit, pushing the next instruction onto the stack, which again is this 005. Now, let's see, we can't see that anywhere. Yeah, okay. So when we go to RAX and we pop off 005, RAX is getting 005, which happens to be a pointer to the string hello world. So now when we return, we effectively have returned the pointer to hello world. Not useful there, but it's going to be really useful in this next one, I think, when we try to print it to the screen, I'm guessing. Yeah, so we're going to, they give us a bunch of tasks here. So first thing we're going to do is we're going to call thingy. I'm just making up random labels. Let's see, so assuming I got a oh yeah, so here we need to pop RSI. So let's not jump ahead here. We're going to call syswrite. So we're going to come up here, the write syscalls number 1. And so to do that, we're going to pass it the file descriptor. So the file descriptor of standard out is 1. I believe. Let's make sure. Yep, file descriptor for standard out is 1 right here. So we need RAX to be 1, RDI to be 1, RSI to be the buffer we're going to write, which we need to get an address of that string, and RDX to be the count. So we'll come in here. We need the write syscall. So we need to move RAX, 1, because we looked it up and that was what that was. We need to label this thingy so that our call thingy makes sense. Okay, so now RDI needs to be the file descriptor, so we're going to move RDI, 1. RSI needs to be the pointer to the hello world string. Well, when we made this call, which moved us to here, we pushed that onto the top of the stack. We haven't changed the stack at all, so we can pop off RSI right there. And then we need to pop off, we need to send a length. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we will pass it move, oops, not 12, RDX, 12, like that. And so that should be fine. And then we'll do our syscall and return. So let's take a look and see if that works. Process exited cleanly with exit code 12. Standard out was hello world. Congratulations. So in case that was, just we'll walk through it in the debugger because it's interesting and it's an important concept. We're starting off with this call instruction that's going to push the return address, which is not really, we're never going to return to it. If we don't call return before we mess with the stack, then it's not really a return address, but it is the address of hello world, which is what we're looking for. So when we do that, we then, you can see onto the stack goes this 005, which is where hello world is. And then we move on here, we set RAX, we set RDI. Here's where we pop off the hello world pointer into RSI. We need to move into RDX, the length of the string, hello world. So we do that. We make the syscall, which prints hello world, and we return. All right, opening a file. So this is where we're starting to get interesting here. We're going to do a couple different syscalls, and let's see. So we're going to get a reference to the string in the correct register. So we know how to do that. We'll come up here. We'll do call and please let's do an ipsec homage subscribe, and then we need to make that label exist. So we will come down here and please subscribe. There we go. So now we need to, oops, that's not where the colon goes. Okay, so now we need to, let's see, get RAX to be the correct syscall number. So we need to open. Open is 2. So come back here, move RAX 2. Set RDI to the first argument. Let's see, is that what that is? The first argument of open is the file name. So we know that is going to be pop RDI because it's on the stack, because Etsy password is on the stack from our call here. Then we need to set RSI to the second argument for the flags, and it says 0 is fine. I could go into, if we wanted to, let's see, this is the open. Linux open syscall. Come to the man page for open, and we could see what those flags were. So we could open it read only, write only, read write, etc. As well as there's also these different append, create, etc. flags. But we're just going to use 0. I wonder what 0 actually is in here. Anyway, let's not waste any more time on that. We're going to go with 0. We're going to set the third argument for the mode. Move RDX kind of 0. And we'll perform the syscall. And so now, at this point, the syscall is going to return a file handle, which is going to be an RDX. And we're going to stop here. We'll see in the next one what we actually want to do with that. So we'll execute it. Great work. Let's read it. We've learned how to read from we haven't actually, next up we'll learn how to read from the file. Right now we just have to open it. So when we make this syscall afterwards, we get back 3, which is the file handle for what we just opened. So we can do stuff with that. And this is where, I think the next step is probably the last one. We're going to read a file. And this is good. So what we're going to do in this one, if I remember correctly, is we're going to do the sys open. We're going to do the sys read. We're going to do a sys write, and we're going to read a file into somewhere. The stack is a great place to do that, and then we're going to write that out to standard out, and that will basically it's effective. How do we use shellcode to read a file? So var north pole secrets.txt. We are going to call leave comment, and then down here we will leave comment. So we need to first call sysopen. And so to do that, let's see, we're going to pop, if we come back to our sysopen reference here, we need RAX to be 2, RDI to be the string here. So we'll do move RAX 2, we'll do pop RDI. We haven't messed with the stack since we made this jump here, so that's good. What else do we need for open? Flags and mode, we can make 0, RSI, and RDX. So we can move RSI 0, move RDX 0. And now we've effectively, oops, it'd be helpful if I add the commas. Oops. All right, that looks good. And now we can do syscall. And when we're done, at this point, RAX is going to be the file handle. So now we need to call sysread on the file handle and read it into RSP. And we don't, not into RSP per se, but the RSP address is the top of the stack. We're just going to start writing down it. So let's do that. So we need a sysread. Sysread is 0 into RAX, the file descriptor into RDI. Now, before we move something into RDX, it's holding the file descriptor. So what we want to do is move RDI, RAX. So now we've copied our RAX into RDI. Now we can do move RAX, 0 to set that to 0. Next, we need to, what are we trying to do here? Read. The next thing is the buffer and then the count. So let's come up here. The buffer is going to be, have we gotten the buffer yet? We have, oh, the buffer is going to be the stack. We're going to do the stack. So I already lost track. What variable are we on here? We are looking for buffer into RSI. And we're going to put the RSP, the address of RSP in there. That'll be nice and easy. And then we need to move a length into here. And let's see, into RDX. And we'll just read, I don't know, 10,000. Might be a lot. I don't know. Syscall. And so at this point, I believe we have called sysread on the file handle and read it onto the stack. Okay, the next thing I'm going to do is write that out. Back out. So when sysread, again, we can come back here. We can do Linux read syscall. See if we can get a man page for that. The return value for the read is a size TT. The return value on success returns the number of bytes read. So that's nice because now we know the length of what we read. We don't have to just guess 1,000. So we want to save that. And if we look at syswrite, the number of bytes to write goes into RDX. So we'll come down here and we will move RDX, RAX to copy what's in RAX to RDX. Now we'll go back to we want to get RAX to 1, the file descriptor, which will be standard out, so also 1, and our RAX and RDI will both be 1. The buffer we're going to write is RSP. We're going to put that into RSI. Move RSI, RSP. And I believe we already set RDX, which is the count. We're good on that. So now we can just do syscall. Now they want us to call sysexit. We know how to do that. We'll exit. We'll see. We'll move RDI, 0. Move RAX, 60, I believe it was. We can go back and check that. And syscall. So these aren't to do anymore. Not that it really matters, they're just comments, but let's make them look nice. Let's give it a run, see if it works. Beautiful. Success. You wrote some. We used Shellcode to write a file. And so you can see we wrote the secret to KringleCon success. All of our speakers, organizers, providing the gift of cybersecurity knowledge, free to the community. So hopefully that makes sense. I don't think it's worth it to step through every step with the debugger here, but we can go back and look at the shellcode. The first trick we need to do is we put this string on the stack, or just it's in our shellcode really. And then right before it, we put a call, and that call jumps down here. So we never actually have to run this, which is good because that would crash. But in doing so, that pushes the address of this onto the stack, so we can then pop it off, in this case, into RDI for our sysopen call. We make our sysopen call. We then take the result, which is in RSP, or in RAX, and move it into RDI so that we have the handle, so we can make our sysread call. And we read an arbitrarily large amount of stuff. The result we store in RDX, which is how much we actually want to print. We then set up a syswrite call to standard out, and we call that, and then we make a nice simple sysexit. So that, is the challenge. The thing they're actually looking for here is, I believe, It's this phrase here is what actually goes into the badge. So actually we can do it. Let's see. What are we looking for here? Objectives, shellcode primer, providing the gift of blank free to the community. You can write this without even having solved the problem. The knowledge. Oh, and it's not correct. Okay, well then I guess I do have to. I get snarky and a gift of cybersecurity knowledge. Grab that. You cannot guess that without solving the problem. I'm sorry, CounterHack. I was being snarky for no reason. And there we go. We solved the problem. So that's gonna be it for the shellcode primer. Hopefully you enjoyed this, and we'll talk to you in the next video.